Good evening, everyone. Today I'm going to talk about custom LED lights for RC airplanes. So this is RC airplane I just added custom LED lights to. For this one I went for 3-watt LEDs that I'm driving at half a watt each, and I have 15 of them on the plane. So before we get into the explanations, let's just turn it on and see the results. So here I got everything all lit up. As you can see, there's 15 lights. Before I talk too much more, I got the garage lights on, so I'm going to shut those off so you can see just how much light it puts out. There we go. As I said before, there's 15 lights on the plane, 5 on each wing and 5 on the main fuselage. So little tour, we have some pointing up at an angle here to light up the fuselage on both sides. Same thing for the tail and the elevator. I should say rudder and elevator. We got some centered lights here and below and in each wing. And then we have some red lights on one end and green lights on the other end. And then finally we have some landing lights, one in the front and one on each side. So what I'm going to do in this video is talk a little bit about how to design one of these, give some alternative ways that you might want to do it, and dig into the electronics a little bit. I'm going to try to make the electronics somewhat accessible for someone that's not as experienced, while not being overly boring for someone that is. That's a pretty tall order, but I'm going to give it a shot. Okay, so now we're going to talk a little bit about the electronics background. This is a program called Fallstad that lets you make circuits. So this is how we're going to demonstrate things. So we'll start with a voltage source, okay? And you can change the voltage. So we're going to make this look like a battery. So we'll just say sliders, voltage, and actually, to start, we'll say -10 to 10, so I can show a couple things. And then we're just going to add a resistor. And there we go. So you can see current flowing through. You can turn this just to change the animation speed. It doesn't affect anything else. And this is a resistor. So the way resistors work is like this. More voltage equals more current, and the amount of resistance determines how quickly that happens. It's just classic Ohm's law, V equals IR. So we can see that. We can give it more voltage, it goes faster, less voltage, it goes slower, and it will even go in reverse. Okay? Let's switch to the diode. So we're going to be using LEDs, which are lead emitting diodes, and they are the same as diodes except for they have different voltage drop and things like that. So we'll just start with a regular diode. So let's just put that in there. And this is the IV curve for a diode. So you can see the resistors aligned like this. A diode is actually quite a bit different. So it blocks reverse current up to a point, and it takes a while to get started too, but once it gets started, it shoots up very rapidly. So let's go ahead and look at that. So just to make it a little bit easier to see, I'm going to change this from -1 to 1 just so I have more resolution. And let's go ahead and add in a test point so we can see what voltage we're at. Okay, so here we're at 400. So at 0, there's nothing. Negative, you won't get anything. Just like it shows, it blocks that negative voltage to a point. And then forward, so here I'm at 140, you're not seeing anything. 180, 200, 260, 280. Let's add a graph for this. So it's starting. Okay, now we're going. And very rapidly, it's like going crazy. So now we're actually putting, at 1 volt only, we're putting 42 watts
which I can see down here, through the diode, which is more than enough to fry most diodes. Okay, so that's a problem that we have to solve. Let's change this to an LED. Same thing, except for the forward voltage on an LED is actually a little bit higher. So we can change this to LED, and you can see the forward voltage for LEDs depends on the color, um, but red is about 1.5, and then white is in the 3 range. Okay, so let's change this again, and we will say the -1, sure, the maximum 5 or so. You can see I'm going up a little higher. Now it's starting because this is a red one. And then same problem. You get up a little bit of volts and we're already pushing 19 watts. So we fried this thing. Okay, so how do we solve it? What we want is less current through here. The easy solution, let me add one more thing in here. An ammeter so we can see. And then we will look at this in the scope. Okay, so we're running 7 amps. So we need to set this voltage. Oh yes, let's talk about how much current we want to run through this thing. Um, so there's different types of LEDs. Um, we're going to use power LEDs. So power LEDs usually take around 300 milliamps. You'll have to look at the spec sheet. Um, but there's a trade-off. At 300 milliamps, they actually run pretty hot, which means you're using up a lot of energy in heat, and also you might be melting things like foam that the LED is connected to. So I don't recommend driving these things at their max rating, but instead driving them at less. So between 150 and 200 for a 300 will still give you plenty of light. You might not even be able to tell the difference, but significantly less heat. So as you can see, I'm having a lot of trouble controlling this. Um, so how do we control it? Well, to start, let's go ahead and make this more of a real battery. So we're just going to make it, um, let's go with a 3S battery. So 12.6 would be our max voltage. Minimum voltage is going to be around 10. Okay, so we'll run this, and yeah, we're already running 173 amps, way too much. Okay, let's fix it. So the easy way to fix it is to add a resistor. So the resist, you can add it on the top or the bottom side. Traditionally, you go bottom side because it makes it easier to measure the current if you want to. Because like I said, um, current and voltage are related by resistance. So if you know the voltage, you can do a little bit of math and figure out the current. Pretty neat. All right, so we'll start with 1K. All right, so now we're running 8 milliamps. Uh, like I said, we want around 200. So let's just change this value a bit. Maybe 200. See what that does. That's not going to be enough. How about 20? 20 is a little too high. 25? 40? Yeah, 40 is good. Okay, so we got our 100 or 200 milliamps. So all is good, right? Well, not necessarily because um, running 200 milliamps through a resistor generally will create a lot of heat. So in this case, if I hold my mouse over there and you look at the bottom, we're running about 1.5 watts, which is enough to destroy most resistors. Now, you can absorb that much if um, you can connect multiple resistors in parallel to divide the load, and you can buy power resistors. So it is a solvable problem. Um, but before we look into how to solve it, because there's a few ways, I want to talk about one alternative real quick. So one way to solve it is to to use a different design. Instead of using a resistor, we're going to use a switching regulator. So they make these right here. This is called a femto buck. And what it is a buck converter. So it takes a high amount of voltage, however much you want to give it, up to 36 on this side. And out the back, you get your current to drive an LED. And it's very efficient, 95% it says here. So a lot of your energy that was lost to heat in our circuit will not be lost to heat here. And it's adjustable with a couple of setting resistors. It's a great thing, and I've used it in planes with success. But there's a downside. Because it is a switching regulator, that means that it has a square wave that's being generated at fairly high power. And that creates two issues. One is power noise. So power noise means that this thing is not sucking continuous power from the battery, but it's sucking it in rapid pulses. And that noise can be seen by servos and other electronic devices, and it can create jitter and other issues. And the other problem is on both sides, especially the input side, and this itself, we're going to have what's called EMI, electromagnetic interference. So basically this thing's going to be making radio waves as it runs, and those radio waves can interfere with other things on the airplane. The most concerning, of course, being your receiver. It might reduce the range of your flight, or it might cause dropouts, things like that. I'm not saying it's going to, I'm just saying by the very nature of it, those are the kind of problems that can come up. So if I was to use one of these, I would either go with a plane that I can stomach losing, or I would do a lot of testing. So the third solution, the one we're going to use, is to not use this design and to try to improve this design. Okay? All right, so improvement number one. Let's add more LEDs in the string. That's a very easy improvement that's going to give us a lot of bang for our buck. So instead of using one, let's use 5 maybe? And of course we'll have to change the resistor because each one of these is going to drop the voltage a bit. Okay, so we got 5 of them in there. And let's go ahead and add test points at each point so we can see what the voltage is, and then you can kind of get an intuitive idea of what's happening. Okay, so let's run it. So now we're only running 20 milliamps, and you can see that each one is dropping some of it. So we're getting more light for our power budget. And we are also down, this one's down to 14 milliwatts, but to get it back up to 200, we'll have to reduce this to like 1, even less, 0.5. We can't get up there. I guess I added one too many LEDs. So we'll just get rid of that and add this in. Okay. 2. It's like 5. No. 7. 8. Okay, pretty close. Okay, so now we're running 344 milliwatts, which is still too high for many, but we can take two, 20s or something, or 320s, and put them in parallel, and that will spread out the heat. Okay, so we're pretty good there, but now we have another problem. You can see the battery's at its lowest voltage here. When you actually plug it in, it's going to be up here, and then you can see the amount of current varies quite a bit. And on the high end, it's actually too high. So we'll have to make this higher to compensate. Okay, but now as the battery lowers down, we're getting quite a bit lower. Um, you might be able to just live with that and call it a day. 98 to 200 isn't like, I mean, you might be able to notice it, but it might be less noticeable than you think. Um, but there is yet another way to solve it. So that is what we're going to work on next. Okay, so what we want is a constant current source or sink, which means as this voltage changes, this current will stay the same. So a source would be on the top side, a sink would be on the bottom side. Traditionally, a sink is usually more common because it's a little bit easier to design. So that's what I'm going to go with. Okay, so we want to keep this, but we can lower the value to like 2 or something. And the key component is a NPN transistor. So this is going to allow us to vary the current and have a current sink, as I will demonstrate. Okay, so we're just going to hook it up, and I'm going to, just to start, we're going to use a voltage source here that will vary from 0 to 10 or so. Okay, and then we also need to add a ground, only so that this voltage source and this voltage source are tied together. All right, so let's start at 0 volts and go. Okay, so you can see that there is nothing going through. But as we slowly increase using this slider, it'll increase this voltage. We are dialing it in. Okay, so there we go. Just a little bit of voltage, and we're already at around our 200 mark. Okay, so here's the cool part. So we're at 12.6. As I lower this voltage, look at the current. Not changing at all. Look at that. That's what we want. Okay. Now this doesn't solve our heat problem. It helps because now this is going to be absorbing some of the heat and this is going to be absorbing some of the heat. But you can see this thing's emitting almost a watt of power, 800 milliwatts. Um, so there's still heat here. And as I lower it down, the power that it emits becomes less because it's got less voltage to drop. So now it's at 266. Okay, so we have a solution, but we haven't fully solved it because this little thing here is how do we come up with 1.2 volts? Okay, so there's a number of different ways to do it. They sell these voltage references, so you could do that. So in this model, it looks like a Zener diode. So we can start with that. So we have a Zener diode. Okay. And you can buy them at 1.24. They sell them in that. Okay, so what a Zener diode does is it's like a regular diode, except that regular diodes, if you override them in the backwards direction, it usually destroys them, where Zener diodes are actually designed to be run that way. So what I'll do is get rid of this, and I'll drop in the Zener diode. Yeah, and now we don't need this anymore. But we do need to connect this like this. And then we need to make sure that we have enough current going through there. Okay. And let's run it and see where we're at. Okay, so it's at 1.2 and that's at 2.5. So we could actually build this circuit and you can see that we're running really well. Okay. All right. So let's talk about an alternative to this little section here. They actually sell this chip Um, here's one of them. They sell many, of course, that basically puts all of the parts into a chip to make it convenient. Instead of a Zener, they use 2 forward diodes, um, which in this case makes a lot of sense because these will be temperature coupled, which we'll talk in a minute. The main downside of using this chip is you'll have to make sure that you get the heat away from it, heat sinks or something like that, because if it's running at full power with a lot of voltage drop, it's going to be getting quite hot. Whereas in this case, you can spread the heat out among several components. So you can make either one work. It just depends on which one you want to go with. All right, so let's talk about the problems and then we'll wrap up. So the problem with this is it's open loop. This is just setting the voltage to 1.25 and expecting it to work. But different transistors have slightly different voltage drops from here to there, from base to emitter, which is going to affect the current. But let's just say that as this thing heats up, or you pick a different one, like you build 2 identical ones or something, this and that changes, which changes this current here. So you can see variation. So to solve it, you need feedback. So I'll add feedback. And while I'm at it, I'm also going to add the ability to adjust the voltage. So let's start with feedback. So a classic way to do feedback is with what's called an op amp. So we're going to put in an op amp here. Active building block op amp. Okay. So the way an op amp works is it senses the voltage on the negative without changing it. It senses the voltage on the top without changing it. When I say without changing it, it means little to no current is going in. And then it takes the voltage at the top, subtract from the voltage at the bottom, multiplies it by a very large number, like 100,000 or something like that, and that's what you see out the output. Um, this thing can't create more or less voltage than you're giving it. So in this particular case, you would never get above 10.91 and never get below 0. Um, and you probably wouldn't even get that high. It just depends on the op amp. But it doesn't matter because we don't care about that for this application. So here's how it works. So what you do is we take this stuff and move it to make some space. And then we put the op amp in there, and then a little resistor here. And then the feedback actually comes from here. And I will hopefully be able to explain this adequately. It's actually a fairly deep subject to cover in just a couple minutes, but we'll do our best. So this is a feedback loop. So whatever voltage is here, if these voltages are different, it's going to drive this up or down. So say that's higher than that, then this is going to go up, right? And as it goes up, this is going to let more through, which is going to increase that, which is going to push that up. And if this is down, this is going to be less here, and that's going to make that go down, and that's going to make that go down. So it's a feedback follower. So that part's pretty good. So we could actually put that in right now if we wanted, and let's go ahead and do that. Okay, so we got that, and then we just run it. Oh, gotta connect everything up, and then we just run it. And you can see we're a little higher, but that's because we have this feedback in there that is helping things out. Okay, so if we wanted it to be a little bit lower, we could just increase this resistance slightly. Let's try 3 or something. 4, 5, okay, maybe 6. Okay, so now we're back where we want to be. Okay, and we're doing about 1/4 of a watt, a little more than 1/4 of a watt. So that's still a little high here, but you could see that the current is going to be nice and stable as we change the voltage, and this is going to be temperature stable as well. So basically all the problems that we talked about so far have been fixed. Okay, so the only thing left to do is make this thing user tweakable. So the way to do that is, well, there's multiple ways, of course, but the way I'm going to do it is by adding in a potentiometer. So potentiometer, that's a variable resistor. Okay, and that goes there, and this goes, oops, and that goes there, and that goes there, and this needs to move up. I don't really need that. Okay, and there we go. And we maybe put the test point here. Okay, let's run this. Okay, so now, oh, let's cook this up. Okay, so we got 100, but now we have this little guy that we can use. Oh, this doesn't need to be 1K. Let's make it 10K. It doesn't really matter what it is, because like I said, the this doesn't pull in any current anyway. So we're just setting a voltage, and that voltage will try to be equated here. So now we can take this back down to 2. And now we can control it like this. So I can just move this up and down and change the target for the op amp. So I'll just set it to, say you want 150, you can just set it to 150, and then it's stable throughout multiple voltages. Or say you think that 250 is what you want and you can deal with the heat, turn it up a little bit, and as you can see, it's still stable. So that is the design, the basics of the design that I'm going to go with. You know, like I said, all this time, there's a bunch of different ways to do it. They all have their trade-offs, simplicity versus heat control versus adaptability versus noise, all that. This is one of them. So hopefully I've given you enough information to at least understand the basics and pick a direction. So on to the next step. Okay, so this is the actual circuit that I'm going to use. It's pretty similar to the one that I've been demonstrating, except for instead of having one transistor, we have 3, because there's 3 strings of lights with 5 each. So you don't see the LEDs in here, I just have the connectors, but there'll be LED strings, just like we had in the false stud model. We have our op amp and we have our potentiometer. And then the particular chip that I chose has 2 op amps on one chip. So according to the specification, we have to tie off the other one so that it doesn't create issues. The issue, or I should say the battery in this case, is a 4-cell battery, and that's connected directly to both the positive terminals and the op amp. And then we sense off one of the transistors and we drive the same voltage to the other 2. This is not the perfect solution since they'll be slightly different, but it's close enough and it saves on quite a bit of parts. All right, so that is the schematic, and then we'll take a look at the PCB. So this is the PCB with the ground fill. I'll turn off the ground fill so we can see the wires a little bit better. And you can see here's our 3 transistors, here's our connectors for the wires, here's our resistors. In this case I'm using slightly bigger resistors so they can handle a little more power. Here's our op amp, and this is where our potentiometer is so we can adjust everything. And that is basically it. Let's get on to actually building the physical version of this.
Okay, I started cutting out this board. I made a completely separate video on how to do this from beginning to end that I'll provide a link for in the description. But as you can see, here we are cutting. And if I didn't mention this before, I'm doing it this way because I've already modified the design 5 times. And if I would have sent it to a manufacturing service, then I wouldn't have got my latest edits before the order was put out. And also, I haven't even tested this thing yet, so after testing it, I might want to make even more changes. So when you're in this, only going to make one and lots of prototyping needed, this seems to be a good solution. This or using the chemical etch process. And, you know, if I decide I really like the design and want to make a bunch of them, then I'll probably order it at that point. So there it is, all cut out, and it looks good. So the next step is I'm going to add some what's called tinning compound. I don't know if I can see it where I'm standing. Yeah, right here. This liquid tin stuff, it's optional, but it helps to keep the copper from oxidizing. And then I'm going to cut out a stencil to make the soldering easier. So that comes next. There it is, all tinned up and ready for the next step, which is to apply solder via the solder stencil I'm about to cut out. Okay, so now I'm cutting out the silk screen, which I'm just going to use to make the soldering job easier. So you can see it cutting into the mylar there, and you can see it up here doing its cuts. And just like the main PCB, I have a separate video on how to do this that you could watch if you're interested in more details. So I'll just let this finish, and then we can use it. Okay, I got the solder mask cleaned up and clamped down, and I got some solder paste. So you just put the solder paste on, and then I'll put it on a hot plate. Okay, I put on what I think I could put on, and I'll just hand solder the rest. So this hot plate is just heating up the solder and setting things, so it'll do a lot of the work for me. And then I just got to finish up with a soldering iron. All right, I got everything hand soldered on there that wasn't taken care of, and I tried to clean it up. Before I go too much further, I'll just have to test all the connections to make sure that everything is connected and nothing's shorted, and then we'll be ready to do some more live tests on it. Okay, so these are the LEDs I'm going to be using. Oh, I just got them off of Amazon. I don't know if they're the best quality, but I've been using them for a while and they seem to be fine. So here they are, just hooked up in a little line. On the real airplane wing, of course, they're going to be all the way across the wing with wires. But I need to test this thing before I get too far. So I'm going to use this little string here. They're just touch soldered together to test that guy. And then after I'm sure that it's working as expected, then I'll just take these apart with the soldering iron and use them in the real plane. Okay, so I got everything all hooked up so you can see the unit and you can see the power. And right now I'm pulling 280 milliamps through this and using up about 4 watts. So we're going to experiment with this, which should allow us to control the power. So let's see how that works. Yep, it works. So I'm turning it down. So that's turned down quite a bit. And you can turn it up. So you can just set it at a level that you think is good. So I guess for now I'll just go with maybe 150. We'll try that. And as I raise the voltage, it should not go above 150. And it is not going above 150. Staying right where it should be. So I'm going all the way up to 16.8. And that's the max right there. So even at 16.8, it's at 150. So it seems to be working just like it's supposed to. So as we lower the voltage, it stays at 150. But of course, at some point, it's going to not be able to keep up because there's going to be more voltage drop over the diodes than I'm giving to the unit. So you'll see it start to go down very soon here. We're still at 150 at 14 volts. Okay, there we go. Now we're losing it. In the 13s, we start to lose it on this guy. So that's 11 there. But in real use, we shouldn't ever see that. So there we are at 16.8. And it looks good. So right now I'm printing those 45-degree little LED holders for the cases where I want to mount the LEDs at an angle. All right, they're done. I went with clear because it was the only color I had other than this orange color, and I don't really want them to stick out on their own. A little bit of stringing between them, but it's a pretty trivial thing to clean up. So yeah, there they are. Okay, I got one wing done. I kind of regret having the wires showing on top instead of the bottom, but I'll just do both sides that way so they look the same. I'll get over it. If I ever build another one, I'll put it on the bottom. Anyway, I'm just have my power supply set here to power it directly. So that's what it looks like. Turned on with 150 milliamps, which isn't too bad. So yeah, bottom side looks good as well. So yeah, I'll just do the other side the same way, and then we'll do the center. All right, evening has come, so we can take a look at what this thing looks like in an otherwise dark room. So you can see it lights things up pretty nice. And there's lights underneath, so you can, when you're coming in for a landing, you can see the ground. I hope you found this video useful and interesting, and if you did, I have a number of related videos where I go more depth into things like the PCB creation process with a CNC and other electronics and RC topics. So have a good day, and thank you. Bye.